ourselves. We have Jason, Varun, David, Elton, Harsha. My name is Isaac. So we would like to thank Dr. Stephen Tullis, who is our project sponsor, and the St. Catherine's Rowing Club, who's helped us out with testing. I'll go through some background information before we get too in-depth. For those of you who don't know about rowing, the rowers sit facing opposite the direction of travel. So to steer, they have to turn around to see where they're going. This can be distracting and cause a loss of power. We aim to eliminate this distraction. So our system will be operated in FISA standard courses, which have lanes that are 13.5 meters wide and buoys every 10 meters. The buoys can be either yellow or red. Our objectives for this project were to develop a system that would identify the lanes, display and highlight these lanes to the rowers, control the rudder position of the boat, and if there's an error, surrender rudder control back to the rowers. We now have a quick video demonstration of what the rowers would see given our project. So you can see the lanes are highlighted in yellow on both sides, and there is a center blue line marking the center of the lane. At the top, there is a turning suggestion, and if there is any warnings, they'll also appear on this screen. So back to the slides. Before we began our design, we wanted to see existing solutions and what was out there. We only found the one by Hindsight Vision Systems. They have a wireless camera and monitor, but unlike our system, they do not control or suggest steering, and they also don't identify lanes. So now, Harsha will take us through some of our design challenges.
Thank you, Isaac. So I'll be talking about some of the challenges we faced along the way. The solutions that we developed for these challenges will be detailed further in the presentation. So firstly, we talked about where to position the camera and how to extract that information. So we decided to put the camera at the front of the boat and at the height of 3 feet off the water to still fit in within the regulations. And if it's too low, then we wouldn't get enough information to work with. And also we used an initial measurement unit to level out the horizon so that we could extract the information better. Then we had difficulties with buoy detection because, as we all know, buoys are subject to be affected by water, wind, and waves, right? So in this situation, we use our algorithm called the buoy placement prediction algorithm that initiates itself based on linear regression. That'll be explained further later on. So when we expect the lane to be entirely straight, sometimes we could have lanes that are crooked, something like that on the left. And what do we do in case of obstacles, such as seagulls, for example, that sometimes pretend to be buoys, I guess. In this situation, we use our masking system that filters out obstacles such as this based on color. And also, it also uses the linear regression model together. And what happens when we have unpredictable lighting? When there's too much light or too little light, our masking system will filter out the buoys accordingly using the color scheme. And Varun will finish off the design.
Thank you, Harsha. So regarding water exposure, it was a major concern for us, and hence we had to make sure all of our hardware components were either waterproof or held in a waterproof container. This is important as this could cause power outage, which could lead to system failure. Liquid exposure could also affect the camera's view, thereby limiting the number of objects that can be detected, and hence causing the tracking to be inaccurate. What helped us solve the problem was testing for errors and making sure that the hardware components were properly placed. The steering interface is the phase 2 part of the project, and this time we used a Raspberry Pi. The system uses linear regression to accurately predict the trajectory of the boat by using past buoy positions. This information is then sent to the microcontroller, which is then processed and then sent to the stepper motor, which then tells the rudder to turn at a given angle. Hence, we had to make sure that the buoy positions were being accurately detected and the algorithm was efficient. The challenge we faced here was making sure that measuring the efficiency of the algorithm and making sure that the trajectory and the rudder control satisfied all of our requirements. And lastly, the processing power is a major concern for us as the Raspberry Pi cannot handle a lot of data. In the beginning, we had problems with picking up the buoys in time in order to give the rowers enough time to react. This is a problem as this could cause the linear regression model to fail if not enough information has been picked up. Over the duration of the course, we did find ways to be more efficient in picking up the buoys, but this is a design challenge that must be worked on throughout the duration of the project and in the future. We also have to make sure that the system is portable so that it can be moved from one boat to another. And now Elton will talk about the engineering details.
So to go over a few of the details, we're going to be going over some of our methods for our image recognition and object detection. So I'll go first through our image processing. So there's two major steps to our image processing. First is putting the image to grayscale, and after that we apply our mask to it. So here's a diagram that shows the whole sequence of steps, and I'll go over some of these in the next few slides. So here we go on the left here, we've got the original BGR image, that's from the camera, and in this red circle is the buoy that we're detecting. We extract the red color channel to get a grayscale image where the buoy appears white. Then we run this through a threshold, which gives us this binary image on the right there. So first, with our masking process, we have an initialization phase where we can, based on the height of the camera, the conditions of the course, such as light conditions, we can change some of the settings to give us, one of the things it gives us is our mask here. So that's our initial mask. And through as it detects buoys, it begins to adapt the mask to limit the range so that we can get rid of things like external, for example, the lane beside it won't detect the buoys from that lane. So before masking, we have this image, where we have the sky and some other noise just in the image, and then the final image just has the buoys in that black box there. And here we'll go to Jason, and he'll talk about how we deal with that data.
Thank you. Even the image is processed, this data cannot be used by the system directly. Therefore, data processing phase is required. First, data processing phase is buoy coordinate extraction. The left picture shows the filtered buoy images. White images shows the filtered buoy images. And to use this image data, system extract is the center of each buoys, and this is considered as XY coordinate of the buoy in these images. You can see the extracted data on the right picture. With this extracted data, it is possible to perform linear regression method. The early stage of the development, we consider the two different linear regression methods. One is the lowest linear regression method with two-case method, and the second one is the least square regression method. And we decided to use lowest linear regression method to provide reliable output. You can see the difference between two methods in this picture. The green line represents the result of lowest linear regression, and the red line represents the result of the least square regression method. There was 10 buoys in the images, and it is not possible to see because it is covered with the green line, which represents the lowest linear regression method provide correct line of best fit, whereas the red line fails to provide the line of best fit. And the subsystem layout will be explained by David.
Thanks, Jason. All right, so for our subsystem layout, as you can see, we have a simple diagram here of the rowing boat. On the left, we have the bow and where our camera is placed. This is looking ahead of the boat at the lane ahead in the direction of travel. Further down towards the stern, in the stern seat, this is the last rower's position of the boat closest to the stern. We have the display. This is what's showing what the camera sees in front of the boat, and as well as the map overlay from the image identification system. Next, we have our CPU case, which contains our Raspberry Pi. It contains our driver for our actuator, as well as an orientation sensor. That then shows the display on the overlay, as well as controlling the actuator on the stern rudder to control the movement of the boat. So here is each node or each subsystem of our system. First we have on the left here is our camera. It's a Logitech webcam. Next is our CPU case. So as I said, this houses all the electronics and all the circuit cards that hold our software. It's rated at IP57, which means it protects all the content from splashing water from all directions, as well as any dust from penetrating the container. Next, we have our manual steering encoder. So this is a 2-to-1 simple gear assembly, which consists of a tiller. This is connected to the foot steering of the boat that all boats traditionally have. And then on the smaller gear, we have a encoder underneath. So in the case of a manual override, the rower can use their foot to steer the boat, which will relay to this encoder and then control the rudder from that point on. Next, we have our display. As I said, this maps an overlay and the image ahead of the boat. Pretty simple. And lastly, we have our actuator, which is a simple model here. So it's just on a pivot. It extends in and out and controls the degree of change of the rudder. So into our hazard analysis, we've identified 2 major risks that can occur during the operation of our system. First, obviously, being the guidance system totally fails. Now, we have a few ways to mitigate this. First, we have our buoy placement prediction algorithm, which basically works as if a buoy is not identified ahead of the boat, the system will look at past data points of past buoys and basically estimate the best position for a buoy and imagine one is there, which will continue to overlay the buoy line on top of that. Next, if the system ends up failing and the boat goes outside of the course, an alert will be displayed on the screen display, and the rower has the option of manually overriding the system by flicking a toggle switch, and again going back to that manual foot control. Secondly, in our requirements, we assume that there would be no loss of power to the system, but in the event that it does happen, the rudder would be frozen in its current position. In this event, there would be a mechanical bias on the rudder, and the boat will be pushing to the left or right, or even straight, depending on where it initially was. This can be overcome by the rowers, however. The rowers can overpower the boat using their oars on either side, and this will allow them to steer for the remainder of the race. Next, I hand it on to Elton for testing.
So, as you saw at the video at the beginning, we had, at the beginning of this project, we went down to St. Catharines and we got help from the rowing club and took a bunch of video of the actual course, which was a FISA-regulated course. That was what we used to develop our solutions through the winter when the course would be closed. Then coming up into the end of the project here, for our real-time tests, we ended up taking it out to the field and we made our own course. We made buoys and we put it to scale, and that helped us make the software work in real time. And now in front of us we have a little smaller scale version of that same test that we can show for you. So on the screen to your left we have a view of the rudder, and on the screen to your right we'll have a view from the camera of the Okay, so as before, you can see the yellow lines are highlighting the lanes and the blue lines highlighting the center of the lanes, and we have a heading indicator at the top of the screen. So if Jason moves it, the camera side to side, we can see that the lanes, the lanes will correct and the rudder will move. It might be a little hard to see the rudder actually move. You might want to look at the actual tiller arm on top of the rudder. There's the rudder over here, and it's controlled by the tiller and the actuator. Yep, and Michael can show that we've made it robust enough that even on the introduction of obstacles, it will still function. And that about concludes our demo and our presentation, and now we can open up to any questions you might have.
How does your the algorithm collaborate for curves? Like if the lane is curved at an angle?
So essentially what happens is all the buoys in that curve would be within the mask, and it would just find a line of best fit of that curve.
Would your the yellow edges, would they be curved as well?
No, they would still be straight lines.
All right. under FISA regulations, is autonomous steering allowed?
So there aren't, as far as I know, from looking through the documentation, they have a few rules. So for example, within the, one of the first things we consider things like beam riding from like the beginning to the end of the lane or using GPS, but they have rules in place for external communications, so that kind of ruled out those options. When it comes to an autonomous steering, there isn't rules yet, so that's kind of the idea there.
Would it be coxless or cox?
So these boats, it's
I mean, obviously this is working with coxless thing, but would you count it as having a cox?
in terms of regulations, I don't think it would be considered as a cox. The system is meant for boats that do not have a coxswain. For those that don't know, coxswain is basically the person that sits in the back or the front of the rowboat and is just there for steering, counting strokes and such. So like I said, this system is meant for smaller boats. So these would be for boats that are 4 people or less without a coxswain. If we choose to continue to integrate the system, we have figured ideas that this could be used in a replacement to a coxswain, but our primary objective is just to use it on non-coxed boats.
In terms of your rudder control, do you have any kind of filter so it doesn't oversteer? Do you have any limits as to how quickly you can change the rudder position?
So how quickly you can change the rudder positions?
Or how do you filter that so that you don't cause a boat to steer suddenly?
Okay, I see. So with the kind of degree of motion the rudder actually makes, it doesn't affect the trajectory of the boat too much. So we found that even if you would change it a lot, it doesn't necessarily turn the boat very much at all. So it's even with steering, as Mike can attest to, you kind of do steer with power imbalances mostly, right? Yeah. So the rudder is mostly for small adjustments.
In terms of the performance of the system, how long is it taking to do a complete loop, and is it fast enough to achieve stable control given the type of situations you'll find yourself in?
Yeah. So we did a couple calculations based on the top speeds that we found for different rowing events to see how fast these boats would be moving at maximum, and we calculated, at very steep angles, how long would it take to, go out of the lane, and we found that that was about 1.5 seconds, and our system does operate at that speed. Now, given the $750 budget of our project was the reason we chose the Raspberry Pi, but there were other devices we were looking into. For example, if we run it off of a laptop or something, it's a lot faster, as you saw from the demo video where we were on the actual course.
Thank you very much.